Here's the problem. It says a point charge Q is located just above the center of the flat face of a hemisphere of radius r as shown in the picture. I'll draw that in a minute. What is the electric flux through the curved surface and through the flat surface? And okay, so here's what we've got. We've got this this hemisphere, just half of a sphere, and here's the center of it, and we're going to give this a radius of r, well, capital R, and right here we're going to put, now it says just above the surface. Now when they mean just above the surface, it means so close that it's not contained within this hemisphere. It's above it, but it's just barely above. Okay, so there's Q, just barely above this surface right here. And it says, what are we trying to find? We want to know the what is the flux through the curved surface. And then for part B, we want to know through the flat surface. And this is one of these problems that's, well, it's very conceptual. There's not a lot of calculations to do, and therefore you're going to see this problem on the multiple choice test of the E&M. They love this sort of thing because it requires conceptual understanding that if you get it, boom, you can do the problem in 30 seconds or less. So this is a good thing to know how to do. First of all, because we want to know the flux through a curved surface. Now, this charge right here is putting out electric field in all directions. It's a point charge. Okay, so we have a point charge field like this. And you'll notice that since it's just barely above this, half of the flux is going to go through that curved surface. It's that simple. You have to draw a picture and visualize it and see, oh, half the flux is coming down through that. And notice that these lines of flux are coming out of the curve. Here's the curved surface here. These lines of flux are coming out of it. So when you go, here's your E field, E dot dA, right? There's your little tiny bit of flux. It everywhere comes out, and it's coming out in positive. And so you have positive flux coming out of this surface right here. So for part A, you're going to say it's equal to the charge divided by epsilon naught, but only half of it. The other half goes up. So half of it goes down, so you just divide that by 2. And there's your answer. That's how much flux is going through the curved surface. So there's no really using Gauss's law or anything. It's just kind of drawing a picture and thinking about it. Now for part B, how much flux is going through the flat surface? Well, here's your flat surface. For every line of flux that comes through here, it has to go into the flat surface. So the answer is going to be the same. But the flux is going into your enclosed surface. And we say that flux that goes into the surface is negative. So that's it. That's all the work you had to show. Now, let's talk about why this is negative, okay? This is negative on here because let's take a look at, let's say here's just a little part of your surface, and here's your charge right here, and it's just barely above the center here. And let's take a look at a line of flux that's coming down like this. Let's say right there it penetrates through your flat surface. Well, if you look at this thing, here is your E. Now, what is dA? Okay, here's Gauss's law. E dot dA. And, oh, you don't even need the closed surface. You can just use E times A right now for looking at this little part. Well, here's your E field. It's going down like that, dotted with A. But what is your area vector? Here's my little dA. Let's make this my little differential area, dA right there. You've got two choices. You can go down with dA or you can go up with dA. Right? The area vector is always normal to the surface. Normal, perpendicular, right? And it's either going to be up or down. Now for this, is it going to be up or down? It's going to be up. Why? Yes, because when you have a closed surface, we say, hey, the area vector points away, out of the volume of your closed surface. So here's my volume down in here, so my dA is going to be like that. So there's my electric field vector, here's my area vector, and look at the angle between them. Much greater than 90 degrees. So when you go E times dA times the cosine of the angle between them, this angle is going to be greater than 90 degrees, and therefore will give you a negative value. So this little differential element of flux, this little tiny bit of flux that we're measuring going through this little tiny area, will be negative flux, and then of course when we sum them all together, you'll get a negative value, a negative amp. That's where that negative comes from. Okay? Any questions on that? Okay, very good.